Topic video 1B, Introduction to Microprocessors and Microcontrollers. What is a typical microprocessor? Well, a microprocessor consists of a set of sequential and combinatorial logic circuits, as we mentioned previously. The actions that are performed by these particular circuits is defined by a stored set of instructions or a stored program, effectively. So unlike our fixed logic circuits, a microprocessor can perform many different tasks defined purely by the software that is driving it. So the same microprocessor can in fact be used in many different applications. It's not fixed to one particular application, but it may be fixed to a particular family of applications, depending on the various peripherals that are provided inside the microprocessor. Generally, a microprocessor is implemented on a silicon wafer, a single integrated circuit. So everything we need, the memory, the processing power, the input-output peripherals, are all included on the same silicon chip. Of course, a processor requires memory for storing its data, storing its programs. It also requires support logic and also some input-output. If a processor can't do input-output, then it's pretty much blind and it's mute. So you need to have some means of getting data in and out of the device. So we definitely need some input-output components. So if we show this pictorially, effectively we have a processor connected to the memory and the I/O via these two buses, the data bus and the address bus. The data bus effectively is our bus responsible for transmitting data from the processor to our memory and our I/O. And we have the address bus, whose sole responsibility is to basically address those various elements in our memory. So the address bus is an address will go along the address bus, and depending on that value, it will turn on either a chunk of memory or turn on an I/O device, and so forth. So it's the address on the address bus that defines a particular component to become active, and then therefore whatever data is pumped down the data bus effectively goes to that particular component that's active as a result of the address on the address bus. Okay, basically a processor is the main functional unit on an embedded board. So if you get like a mobile phone, or you've got a PDA or microwave or whatever, it is the processor itself that's the main functional unit, is the main doing component of that board. And it's primarily responsible for processing instructions and data. So we have a stored program with a series of instructions, and we have some sort of data in which that program is going to manipulate that data in some way. So that data could in fact come from some particular input-output device, or it could always be embedded inside the processor. But effectively, it's responsible for processing the instructions and the data. Okay, a basic microprocessor contains four basic sections, and these are the arithmetic logic unit. These are primarily the doing part of the microprocessor. So this is where we have the mathematical manipulation sections. So we have our adders, our subtractors, our multipliers, our dividers. We have our logical functions. We have our movement functions. We basically have the portion of the processor that's responsible for doing things. So it's effectively, this section consists of the blue-collar workers that are actually doing all the work. We then have an interface section as well. So the sole purpose of the interface section is ensuring that the processing core is communicating properly with the I/O devices as well as our memory devices to ensure that data is transmitted in appropriate times, to ensure that we don't have data corruption, to make sure that things are received correctly. So we have a whole section defined purely for ensuring that the processing core is communicating properly with the other components inside the chip. We also have a control section inside the processor as well. The control section is solely responsible for ensuring that we have our instructions coming through into the core at the appropriate times. The instructions are then decoded, and the various functional blocks, the various components of the ALU are actually turned on at the right time to ensure that that instruction can be implemented correctly. The last component we normally have inside a processor is, of course, our registers. This is our register set, and basically consists of some internal memory where we can store variables and data while we manipulate them inside the processor core, but more on registers later. A microprocessor is effectively capable of 6 simple functions, and these are being able to write data to system memory, being able to read data from the system memory, write data to an I/O device of some kind, read data from that I/O device, read an instruction from memory and execute it, and of course manipulate data within the microprocessor. So they are the 6 simple instructions, or 6 simple functions that a microprocessor can do. Basically, when features that are built into an architecture instruction set are commonly referred to as an instruction set architecture. So to reiterate that, effectively a microprocessor is simply a set of combinatorial logic that executes given instructions. So we can give it a series of instructions and it will simply execute them. So therefore, our instruction set itself defines the architecture of the processor. There is absolutely no point in having functional units inside a microprocessor if there isn't an instruction to enable those functional units. So therefore, the architecture of our microprocessor is heavily defined by the instruction set that we have for that microprocessor. So therefore, the instruction set architecture is effectively the instruction set which defines the architecture of the microprocessor. And of course, depending on how quickly you want those instructions to operate, then the architecture of the processor is defined in such a way to ensure that the timing is met for those instructions. So if you want to be able to have a processor that can do very quick multiplies, 1 or 2 clock cycles, then the architecture of the microprocessor has to reflect that. So we have to have very fast multipliers, very fast barrel shifters and things like that to ensure that multiplication happens in 2 clock cycles. So the instruction set effectively defines the architecture of the microprocessor. So the instruction set architecture effectively defines such features as the operators and the instructions, the form of the operands, or the data for those instructions, the storage and addressing modes that we have inside our microprocessor, and of course the way that we handle our interrupts. So when asynchronous events take place and we have to stop what we're doing, we have to service those asynchronous events, how do we do that? So that's all defined by the instruction set architecture. So when it comes to operations, basically with our operations we have instructions or commands. These are the instructions that pretty much turn on the functional blocks of our processor to do certain things. They are processor specific, so there's absolutely no point in having exactly the same instructions on every single processor, because then every single processor would be exactly the same. It is the instruction set that defines the processor, so therefore we're going to have different instructions on every different processor. So irrelevant of whether you learn the Freescale processor in this course, if you pick up another processor, it's going to have a completely different set of instructions, so you've got to learn a different set of mnemonics. So they are very processor specific, and of course they're defined by the instruction set architecture, because you've got to have that functional blocks behind those instructions to make those instructions happen. So with the types of operations, we have computational, so we have instructions for manipulating numbers, we have addition, subtraction, multiplication, division, and so forth, and of course logical operators as well. We also have movement operators, so we can actually move data around from point A to point B. Okay, we need to move data into the processor to be able to manipulate it in most cases, otherwise we want to have it inside memory. So we need to be able to move data from memory into the processor and back again when we're finished with it. So we've got movement operators. We've got branches, because a chunk of code or a program is very rarely sequential in nature. Very rarely just a single instruction one after another in a single line. We need to be able to split and move and branch in such a way when certain conditions are true, we need to run a certain block of code. When it's not true, we need to run another block of code. So we need to be able to, have some sort of conditional mechanism inside our program, depending on certain events that might take place. So we need to have some branching sort of instructions as well. And of course we need some sort of context switching mechanism, so when an interrupt or some unexpected event takes place, we have the ability to stop what we're doing, save our data, and then service that asynchronous event, then come back and continue with what we're doing. So we need some sort of means of doing context switching. So talk about that in a bit more detail when we talk about interrupts. Okay, so when it comes to the operation format, generally with an operation we have it consists of two components. We have an opcode and an operand. The opcode is in fact the instruction that tells us what we want to do, and the operand is the data for that particular instruction. So the operand may in fact be the actual value that we need for that operation, or it can in fact be a pointer or a memory location to where we can get the particular value that we need for that operation. So it can be the actual value we need or a reference to somewhere else that we can then use in order to get that particular value or data that we require. So we have an opcode and we have an operand. I've given an example here of the LDAA command, which is your load accumulate array command, and it has a hash, so it's an immediate operation, so it effectively wants to load the value of 32 into accumulate array. So the LDAA is the opcode, is the instruction that's saying, I want you to load a value into accumulate array. The operand is the hash $32, which says, I want you to load the hexadecimal value 32, this actual value here, into accumulate array. So the operand is the actual value that we want to operate with. And that's generally converted into machine code, because that's the beauty of assembly. It's direct translation into machine code. So if you wanted to actually store that in memory, it'd be stored in hexadecimal format as 8632, or if you stored it directly in memory in binary format, then I've shown that there also as well. So that's the particular instruction, the operand for that instruction, and how it would be represented in memory. So when it comes to operands, operands can be of different sizes. They're generally defined by one of these base types, so irrelevant what sort of operand it is, it'll either be an 8-bit value, a 15-bit value, an 8-bit value, a 16-bit value, or a 32-bit value, depending on what sort of operation is that you're doing. So generally with our microprocessor, the operands are either 8 or 16-bit. And as I said before, the operands are effectively the data that we need to manipulate, or a reference to the data that we need to manipulate. So in many architectures, as I said, operands are simply defined by either an 8-bit, 16-bit, or 32-bit word. And more complex data types such as integers, characters, or floating points are basically based on those very simple types. Okay, so the other thing that the instruction set architecture defines is in fact our storage. So an address space can be characterized in one of two ways. It can either be defined as linear, okay, which means we basically have a linear address space that starts at 0 to the size of our address bus. So in our case, it's from 0 to FFFF, and we simply have a linear mapping. So that's all of our entire data is then, or memory addressable elements are all then within that linear address space. You can also have segmented, and what we have on our processor is we have a combination of linear and segmented sort of storage mechanisms. We have the linear 0 to FFFF, but inside that linear memory map, we actually have windows in which we can refer to segmented memory locations. So we have a EEPROM window, we have a RAM window, and we have a flash window. And using those different windows, we can then see our segmented memory, which gives us the ability to see a bit more than the 65,000 odd memory locations that we would normally have access to. So we can actually see a lot more memory, because of course we have 512K of flash on this processor. We can't really see that inside a 16-bit address space, so we can actually use a segmented address space, and using the flash window actually point that flash window to any sort of 16K page inside that flash that we want. So we have a combination of both linear and segmented on our processor. And I've shown that here in this diagram. So we have on the left, we have our linear memory map from 0 down to FFFF, and inside that linear map we actually have our various Windows for our RAM, Windows for our EEPROM, and Windows for our flash. So therefore we can actually see the segmented, the segmented memory map that we sort of have on the right. So on the right we have a very segmented sort of memory map where we can sort of point our windows to what those various pages inside that segmented global memory map on the right. Okay, so just as an aside about when we talk about memory, processors of course need memory. Without memory, processors don't work at all. Processors need memory to store their programs. Processors need memory to store their data. So without memory, processors just don't work at all. So when it comes to memory, memory consists of three basic sections. We have RAM, which is our random access memory, which is generally our read-write portion of memory. We have our ROM, which is read-only memory. And of course we have I/O devices, which are memory-mapped input-output devices that also sit inside our memory at particular memory locations. And of course, as I said before, data and instructions are stored in memory. So without memory, processors don't work at all. So one of the other things that we actually get defined by our instruction set architecture is, of course, our register set. Registers are very important to a processor. Registers effectively define how capable your processor is in a way. The more registers you have, then the less data movement you actually need to do in and out of memory, because the more internal memory you actually have inside the processor. So register sets are in fact fast internal memory inside our CPU core. So it's memory elements inside the CPU that we can use to temporarily store values while we're processing them in some sort of way. Okay, a register set, effectively it is named memory. Okay, it's not addressable. You can't say, okay, I want memory address 0 and that's your particular register. No, they are named. And by named, I mean there are a series of instructions that operate purely on that particular register. So to go back to the example I gave you before of load accumulator A, that effectively defines the register accumulator A. Okay, so the instructions in fact name the particular register that they want to operate on. Register sets generally a general purpose, or they can have a fixed purpose depending on their function. Generally you'll have a whole array of general purpose registers, but then you'll also have a series of registers inside the core that have a fixed particular purpose as well, and we'll get to talk about them in a second. A microprocessor can of course contain anywhere between a few registers to several hundred, depending on what sort of processor that you're using. So the current Intels that we have actually Intel processors that you have inside your computer have up to about 128 registers, so quite a lot of registers inside the processor, whereas the processor that we're using inside our cores only has a few number of registers. So inside the MC9S12 XDP512 we actually have a register set which consists of 6 registers. So inside the CPU-S12 there is 6 registers. There is a 16-bit accumulator. There are 2 index registers X and Y, which are both 16 bits in size. We have a 16-bit stack pointer. We have a 16-bit program counter, and we have a 16-bit condition code register. So they are the registers that exist inside the core of our processor. We also commonly refer to the register set as the programmer's model, because this is our interaction with the actual processor in a way. We're moving data into these registers, we're doing instructions on these registers, and we're moving data out of these registers back into memory. So it is our interaction with the processor is done via these registers. So when it comes to the 16-bit accumulator, it's a general purpose register. It's the most commonly used register that you'll be using inside the core. It's able to perform mathematical and logical operations. It consists of a 16-bit accumulator that can be split into 2 8-bit accumulators. So if you're dealing with it as a 16-bit accumulator, then you refer to it as its name as D, accumulator D, so you use all the accumulator D instructions. If you want to use it as two separate 8-bit accumulators, then you use all the accumulator A or accumulator B instructions. So depending on what instruction you use, we'll define that register as either 16-bit or 8-bit. And of course, any instruction that you can use on accumulator A is effectively interchangeable with accumulator B. So if you want to do an instruction on accumulator A, but you're currently using it, you can do the same instruction on accumulator B. Okay, the next register that I'm going to talk about is the stack pointer. The stack pointer is a great little register that effectively it is a memory pointer which points to the top of the stack. So a stack is a chunk of memory that we have in our RAM that we use for temporary storage. So simply by, we can push values onto the stack, we can pull values off the stack. So we can push values on the stack, we can pop values or pull values off the stack. So we have a stack pointer that effectively points to the top of our stack, because that's all we really need to remember is the top. So the stack is a storage structure which is a LIFO storage structure, so it's last in, first out. So it's effectively like, as the name suggests, a stack. So as I said, it's used for temporary storage during program execution. The stack is filled, as we fill the stack, it grows in size. So basically, as we remove those elements, the stack shrinks. Okay, so the stack pointer is a 16-bit register that points to the last memory location filled by the stack operation. So it effectively points to the top of the stack. So to give you an example, how a stack works. So just assume that this is like a stack of books, because it's really exactly the same way. So how a processor stack works is the same way as a stack of books. We put down a book. We've got to just remember the top of the book pile, because we want to put another book on that pile, we've got to put it on top of that one. So we just need to keep track of the top. So same way with the stack inside our processor, we just need to keep track of the top. We can put another value in there and it goes on top. Okay, so it's the same thing like a stack of books. We can keep putting values on the top of that stack. So we just got to keep remembering where the top is. Put another value on the stack. Just got to remember the top. Just got to remember the top, where the top of the stack is. So we just keep putting the values on the top of the stack, just need to see where the top is. And then of course, when we finished filling out, we want to take values off, we just got to remember the top. So remember the top of the stack, and we take the value off the top, and we change the pointer to point down to the next value on the stack. And then we take that value off the stack. We've just got to keep track of the top. So same way that you normally, when you're doing a stack of books, you just got to remember the top book when you put the next book on top, or you just got to remember the top book when you want to get the book off. But like a stack of books, the processor stack works in the same way. If you want to get, say, the book that's fifth down, well, you've got to pop all the values off on top of it before you can get to it. So a stack on the processor works in the very same fashion that a stack of books or a stack of plates works. It's the last in, first out. So it's the last one you put on the top is the first one that you're going to get out off the stack. Of course, we grab the last one off, and then we just got to keep our pointer pointing to where our space is that we can stack our particular data or variables that we might want to be using. We'll talk more about the stack operations later on when we talk about the instruction set. So to give you an example with the actual processor that we have, when we do a push A command, which simply pushes the contents that are in accumulator A into our stack, before we do the operation, we have D2 in accumulator A. We have our stack pointer pointing to a particular memory location, which is where C2 is. We simply do a push A, which means D2 still stays in accumulator A because it doesn't move it. It's not a move, it's simply a copy out of accumulator A onto the stack. So basically, the stack pointer is decremented because we already have a book on the top of the stack, so to speak. So we simply decrement our counter, so we move it back in memory by one memory element, and then we put the value of D2 on there. So our stack pointer is actually pointing to the last value that we put on the stack, which in this case is D2. So our stack pointer is automatically decremented by 1, and then the value is actually put where the stack pointer points to. So the same thing when you do a pull A, which simply pull the value back off accumulator A, pull the value off the stack and put it back into accumulator A. We simply have the value of D2 inside accumulator A. We have our stack pointer pointed at C2. And we simply do a pull, which means the value of C2 goes into accumulator A, and then the stack pointer is incremented by one memory location to point to the next value that is now the top of the stack. So these values still stay in their memory, but our stack pointer is decremented to point to the new top of the stack, which in this case 45 sits at the top of the stack now. So you can see in this case, stack pointer simply moves the value that, or the pull operation effectively moves the value where the stack pointer refers to into accumulator A, and then increments the stack pointer by 1. So it's a post-increment operation. Okay, the next register that's really important is, of course, the program counter. The program counter is a 16-bit register. It simply holds the memory location of the next instruction to be executed. So it simply points into memory where our next executable instruction is. And of course, a program counter can only be modified by jump or branch instructions. So you can't directly write to the program register, but you can modify it by using a particular instruction such as a jump or a branch instruction. Okay, the condition code register. This is a register that's very important for telling us the condition of the processor with respect to the previous operation. So when an operation takes place, the various bits inside the condition code register are set depending on what that operation did. So if that operation was a mathematical operation and we got a particular number out of that operation, say it was a negative or a 0 or something like that, then the appropriate bits in the condition code register will be set to reflect what happened in that operation. So basically the condition code register consists of 5 status bits, 2 interrupt masking bits, and a stop instruction control bit. And of course consists of some interrupt priority level bits as well. So with respect to the status bits, we have our half carry flag, our negative flag, our 0 flag, our overflow flag, and our carry borrow flag. So the MSB of the actual condition code register contains only 3 active bits, which are the interrupt priority level bits. These allow nested interrupts to be used, so we can have more than one interrupt running at a particular time, and of course the value in the interrupt priority level defines which interrupt is allowed to complete first. And this is covered later in a subsequent lecture topic. So regarding the status bits in the condition code register, we have the S control bit, which basically setting the S bit disables the use of the stop instruction. So if you set the S bit to be high and use the stop instruction inside your code, the stop instruction is effectively ignored and it does the equivalent of a no operation instruction, which means it does nothing. We have our X mask bit, which enables or disables the external XIRQ pin and the supporting interrupt subsystem that supports the XIRQ pin. So there's an external interrupt pin that's external to the processor, and it is the X mask bit that effectively turns that pin on or off. We have the H status bit, which is the half carry for accumulator A or B. So when you're doing a binary coded decimal and you have a number that goes from 9 in value up to being 10 or greater, then the half status bit is actually set to allow, a subsequent decimal coded binary instruction to then do a correction on it. So if you've actually done a binary added 2 binary code decimals together and you've got a value that gives you 16 greater than 10 or 11 or 12 or whatever, and you need that to be fixed so that the bit greater than 10 actually moves into the next 4 bits higher, then you can, using the H bit, you can then run a decimal binary coded decimal correction command to actually correct for that. So the H bit is actually useful when you're doing binary coded decimal operations on your processor. The I mask bit is actually useful for turning on or off the entire interrupt subsystem. It doesn't affect the X the XIRQ subsystem, but it turns on or off the remaining interrupt subsystem. So it turns off the external IRQ pin. It turns off the serial analog digital converters, timer, interrupt subsystem. It turns off all the other subsystems on the processor. So we turn all the interrupts off simply by setting that I bit. If we clear it, then they're all on. The end status bit, this is set as a result of an operation which produced a negative number. So when we looked at the 2's complement negative number, 2's complement negative number will always have the MSB, or most significant bit, set to be 1. So if you do an operation and it causes the most significant bit to be 1, then the end status bit will also be set in the condition code register. So this is good for checking to see if a result of an operation produced a negative number. You might want to branch as a result of whether the end bit is negative or not. We've got our Z status bit, which is our 0 bit. So if in fact we do an mathematical operation and we get a 0 as a result, or we do a load from memory and the result is 0, then the Z flag is actually set. So that may actually be used in some sort of condition statement somewhere where you might branch if a particular value is 0 or not. Okay, so the V status bit, this is used when we might try to make a negative number out of a number that's too big. So in an 8-bit register, effectively we can only make a negative number out of a number like 127 is the maximum number we can turn into a negative number. If we try to make a negative number out of 128, well, we can't do that. Therefore, the V status bit will actually be set to say that we've had an overflow, a 2's complement overflow. We couldn't actually create a negative number, which means that some error has taken place. So you might want to use that as an error checking mechanism. If you're converting positive numbers into negative, you might want to check the V bit to see if in fact it's created a correct negative number. And of course we have the C status bit, which is our carry bit. So when we're doing additions of multi-word numbers or subtraction of multi-word numbers, it is the C status bit that actually holds our carry or our borrow for us. So it is this bit that passes on that carry bit from the least significant word that we've added together and moves it on to the most significant word. So then when you're adding the most significant word, you want to use the add with carry command to take that carry bit into account when you add them together. You can also use the carry bit to check to see if in fact you've done an addition, to check to see if the carry's set or not, because if the carry's set, then of course it sort of reflects that like an overflow has taken place and some sort of error may have taken place as a result. An index register, we have 2 of them on our core. Basically they're used for indexed addressing. They can also be used as 16-bit general purpose registers, and there are a lot of commands that we can use on these index registers, so they are very good for just simply using as general purpose registers. But of course, if you want to do indexed addressing, then this is the only registers you can use, because they're called index registers primarily because they are used in indexed addressing, but we'll talk about indexed addressing a bit later on. So we have 2 index registers. They're namely called X and Y. And of course, we can use those 16-bit registers as 16-bit counters as well, as if we so choose to. Okay, so with the instruction set architecture also defines our control section of our processor, and the main purpose of our control section of our processor is to implement what we commonly refer to as the fetch, execute, and decode cycle. So what happens with our fetch, execute, and decode cycle is basically, first of all, our processor has to determine our instruction, determine which is the next instruction that we're going to run, basically fetch that instruction out of memory, decode that instruction to work out exactly what it is that it needs to do. It needs to then fetch any operand, so if it's, say, a load instruction, that needs to grab the operand that's straight after that instruction to see where in fact that data is that we need to work with. We may in fact need to, if it's an immediate instruction, we already have that data that we require. If it's a operand that refers to some sort of portion of memory where we need to get that data from, then of course it needs to fetch that operand. So you have another memory read operation to get that operand or that piece of data that we require out of memory. And then of course we execute that particular instruction, which means we then activate the arithmetic logic unit to do whatever it is that we need it to do. And then as a result of that operation, we'll have some result that we need to store Okay, whether it's simply storing it internally inside a register inside the processor, or whether it's storing it back into memory somewhere, that will depend on the particular instruction that we're doing. But basically, as a result of the execution, there'll be some data that we'll need to do something with. We'll need to store it somewhere, either in a register or in a particular memory location in memory. And then, of course, that repeats all over again. So we need to then determine the next instruction, then fetch it, decode it, execute it, and so forth. So we do that whole process in a very circular pattern. So that's all the processor does, simply that state machine moving around in that circular format. And of course, when we get branches, then of course the next instruction we need to execute changes, so therefore we have jumps around inside memory. But basically the processor does that continual cycle of that fetch, execute, and decode. When it comes to our processor of choice, we basically have a two-stage pipeline-like mechanism here. If you go back to that previous diagram with the state machine of the very circular fashion, we actually have a independent section inside our processor whose sole responsibility it is to actually fetch the next instruction. So we're actually independent of the instruction to code and execute sections. We're actually got a separate section that its sole responsibility is to simply fetch the instructions. So this is what we refer to as our instruction queue. He just continually grabs the next instruction, has it in a buffer, ready for the instruction decoder and executor to simply deal with those instructions. So this sort of speeds up our processor a little bit, because we don't have to wait for it to fetch that instruction and the operands, because they're already sitting here inside our instruction queue, inside the processor, ready to be very quickly read when we get around to executing them. So when it comes to this instruction queue, we effectively have three buffers. We have a latch, where it's simply a buffer for holding a next instruction if in case we've haven't advanced the queue, but we've actually asked for a piece of data. We'll stick it inside the latches and wait for the queue to actually advance. We have two stages inside the queue. We have stage 1 and stage 2. And we have a series of demultiplexers to simply connect the various bytes in the stage to the various opcode and the opcode 1 and opcode 2. So generally, the opcode would be the actual instruction, and the subsequent opcodes would be the operands for that particular instruction, whether they're the actual value we require, or whether in fact they're the memory location of where we can get that value from. But basically, the output of the instruction decoder, or the instruction queue, is in fact the 3 bytes that need to be decoded by the instruction decoder. So to give you an example how the instruction queue works, we have a example program here. So we have LDAA 1234, dec A, arithmetic shift right A, and then of course add that particular memory location to A. So we simply, it's not a really very practical example, but it's an example of some various instructions that we can give to our core. I've then shown to the left of that the memory locations and the particular machine code equivalent of those instructions. So the machine code would actually be embedded inside the memory at the particular memory location shown to the left of those machine code instructions. So what happens when we actually start running this code inside our instruction queue is our instruction queue is actually filled up with the first 32 bytes of our program. So we've got B6, 12 in the top line, and we've got 34 and 43 in the second stage. Then what happens is the multiplexers connect, because B6 is our instruction, and 1, 2, and 3, 4 are our operands for that instruction. So they're all latched through in the alignment section so that the instruction decoder can get the instruction as well as the 2 operands that it requires. Then what happens is once it's run that instruction, then it advances the queue. So the queue simply moves up. So everything moves through that queue up to the next stage. So we actually have 34, 43 in the top line now. 34 was the operand from the previous instruction, so don't bother latching that one, but 43 is the opcode for the next instruction. So 43 is latched through. Okay, so we have 43. It's only a single value for that instruction. It's only one. It's what we refer to as an inherent instruction. It has no operand, so therefore 43 is latched through. Of course, the next 2 values would be latched through, but the instruction decoder would just ignore them anyway. So the whole queue advanced up by 1 stage. Then what happens is the queue advances again because we've dealt with that 43 value we had before, and now we've got 47, which is also an inherent instruction. So he simply latches through to the opcode, and of course our queue advances prior to that. But what happens as a result is now we have the next instruction sitting in the top queue already. So we have the top level of the instruction queue. We have BB there already, which is going to effectively stop our queue from advancing because it's already in the top stage. We can't advance it any further. So BB simply latches through, and the next two instructions inside our on the next level of our instruction queue are actually latched through to our alignment, which then pumps through to the instruction decoder. So the queue did not advance in this case, but we requested 16 bits to refill the queue. So those 16 bits come back and they actually sit inside the buffer waiting for next time when the queue advances. So next time the queue advances, it won't ask for another 16 bits to fill it because it's already got data in the buffer. So simply the next time the queue advances, stage 2 will move up to stage 1 and the latches will move into stage 2. So effectively the queue advances, and of course the buffer is latched into stage 2, as I said. So when it comes to the instruction queue works perfectly, works very, very well in sort of very sequential code, when you've got code that simply flows from the top to the bottom and there's no branching or no changes in the execution. It works very well. But the second you start changing that program flow, like you start putting in branches or you start putting in jumps or branch to subroutines or jump to subroutines and things like that, you start jumping around in memory, then of course the instruction queue doesn't work as well. There are other situations that also bugger up our instruction queue, and these are of course when we have a reset. So when you turn the power on and off, then of course it's got to jump back into memory somewhere else, so it's got to jump to wherever the reset vector points to. If you have an interrupt, like a subsystem says, hey, I need you to service this request very quickly, then of course an interrupt's going to trigger, and then of course the processor's got to stop what it's doing, which means it's got to save everything that it's doing, it's got to flush out its instruction queue, and it's got to refill that instruction queue with wherever the interrupt service routine was. So interrupts will also cause havoc to our instruction queue. And as I said before, jumps or calls to subroutines will interrupt our instruction queue as well as conditional branches and of course jumps. So anything that sort of changes our processor from working in a sequential manner will effectively stuff up our instruction queue. So instruction queue works very well as long as the queue is kept full. The second you do a change in program flow, then of course the queue's got to be flushed, it's got to be refilled. There's a slight delay associated with refilling that queue. So of course if the more sequential you can make your code, the faster it's going to run. But of course there are downsides to making code very sequential, is that it's not very modular and it's very, very big. Okay, so we've looked at the control section of the processor, we've looked at the register set section of the processor. Now let's have a very basic look at the arithmetic and logic unit. So the arithmetic logic unit effectively is the brain of the processor. Okay, it performs all the mathematical and logical functions. Basically, it's the blue-collar worker, it's the doing part of the processor. So the arithmetic logic unit can be basically thought of as a black box where we have two operands coming into that box, and we have a series of control lines defining what sort of operation we want to do on those two operands. Generally, those two operands, one will be an accumulator. In our case, it will either be accumulator A, B, or D, or maybe one of the index registers. And of course, the buffer would be some temporary holding buffer. So if you're doing some operation out of memory, then it'll be that memory load into that buffer. So generally, with an accumulator, there's two operands, and there's a series of control lines to define what operation that we're going to do. And of course, those control lines will be coupled to the instruction decoder. So when you give an instruction to the instruction decoder will set these particular control lines to basically cause the arithmetic logic unit to do the particular operation that we want it to do. So of course, out of that arithmetic logic unit, we're going to get a result, and the result will simply be accumulator operated on by the particular buffer. So arithmetic section of the basically the arithmetic section of the arithmetic logic unit contains the logic to implement binary arithmetic, such as addition, subtraction, multiplication, and division. And of course, the most simplest of these operations is of course addition. So when it comes to doing binary addition in digital logic, this should hopefully be a revision, but if it's not, bear with me. The half adder is the basic fundamental block of any adder. It's capable of adding 2 bits together. Okay, so basically the goal of the half adder is to add 2 binary digits based on the assumption that there is no carry input. So there's no ability to carry from a lower bit to a higher bit. So the half adder simply can add 2 bits together. So the truth table of this device is simply if A is 0, B is 1, then the result is 1 and the carry is 0. So simply A plus B is the result that we give out, and of course the carry is of course if the result is greater than 1. So if you case where A and B are 1 and the other bit is 0, then we'll always get 1 out of the result, because it's simply 1 plus 0 gives us 1. In the case where A and B are both 1, then of course we're going to get 2, which means the result in this case will be 0, but the carry bit will be 1. So we want to carry that carry bit on to the next stage. Okay, and then of course if A and B are both 0, then of course the result is 0 and the carry will be 0. Okay, so the half adder is the most primary component of any adder. So when it comes to working out what digital gates actually live inside the half adder, it's quite clearly that the result is simply an XOR, because if A and B so if A XOR 1 will give you the result. So if A is 1 and B is 0, then you get 1 as the output. If A is, and if the inverse is also valid as well. So if one of them is 0 and the other one's 1, then of course our result will be 1. So it's simply the XOR of A and B. Of course the carry bit was only set if A and B were both 1. So therefore carry equals A and B. Okay, so I've shown that in form of the logic gate. So you see that the result is in fact an XOR gate and the carry bit is in fact an AND gate. So that is the half adder, which is by far the most basic of any arithmetic operation. Of course, it's not very useful if you want to add multi-bits together. Then of course you've got to take into account the carry bits. So the full adder is in fact designed to take into account that carry bit from the lesser significant bits. So the full adder has 3 inputs, A and B, like the half adder, but it also has a third input, which is the carry in. So the carry bit from lesser bit additions can actually pass into this full adder. And it produces 2 outputs, like our half adder, the result, the full sum, which is the result, as well as the carry out, which it can then pass up to more significant binary additions. So you can see that the full adder effectively consists of 2 half adders in which the carry bit is actually then ORed together. So the carry bit out of the 2 half adders is in fact ORed together. The first half adder actually adds the 2 inputs together and passes that result down to the next half adder, which then adds the carry bit to that result and then passes that value out as the full sum. So the 2 carry bit outs from those 2 half adders is then ORed together to produce the final carry out. And I've shown that in a truth table as well, but I'm not going to go through all that. You can have a look at that at your own leisure. So we can represent the full adder as either a logical symbol, which simply consists of a black box approach where we have our X and Y as our inputs, we have our carry in, our carry out, and we have our sum. We normally put an FA on it for full adder. You can also show it in gate form, so this is a slightly different gate form to the one on the previous slide, but there are many, many different ways of showing a full adder, because as the saying says, there are many, many ways to skin a cat. There are many, many different ways of doing logical combinatorial logic functions. So even though they do the same thing, you can draw them all completely different ways. So when it comes to using the full adder to do multi-bit addition, we actually simply use a cascaded sort of approach where we add the least significant bits first. So we have a half adder on the least significant bit, we add the least significant bit, we generate that full sum, and we pass the carry out bit into the carry in of the next stage next to it. And then of course we do that summation, we get his result, and we pass this carry out to the next stage. So you can see it's a very ripply on effect where we get the least significant bit, then we go on the next clock cycle, get the next bit next to it, and the next clock cycle, get the next bit, and so forth. So you can see to add up like an 8-bit number would effectively need 8 clock cycles. We need that carry bit to ripple through to the higher, most significant bit values. So it's not a very efficient way of doing it, but what they do these days when it comes to doing addition is they actually have carry look-ahead circuitry, so we can actually beforehand predict what the carry bits are going to be. So on one clock cycle we can predict what all the carries are going to be, and then simply on the next clock cycle pass all those carries down to the addition stages, and then simply add them on a couple of clock cycles. On a couple of clock cycles we can effectively do the whole addition instead of having to wait for that carry bit to ripple through. Okay, so as I mentioned previously, the functions of the arithmetic logic unit, basically we perform arithmetic operations on the ALU on binary data, and we can also use the arithmetic logic unit as a data pathway, so we can simply move data through the ALU, so we can do a no operation with the ALU simply to use the ALU to move data from, say, an accumulator to a particular buffer somewhere else. We can also use the ALU to perform binary and logical operations such as logical shifts, logical ANDs, logical ORs, logical XORs, logical complements and things like that. And of course, like before, what we want the ALU to do is defined by a series of control lines that feed into the ALU. So using a series of full adders, we can effectively create an arithmetic logic unit. So we've got these series of gates that sit around the full adders that allow us to implement a whole heap of different logical and numerical operations. So we can do additions and subtractions, we can do increments, we can do decrements, we can do lots of other wonderful things simply by driving the 3 control lines. So we've got K1, K2 and K3, which are our control lines, and by setting them to a particular value we can actually define a particular operation that we want this arithmetic logic unit to do. So we can set our 2 operands x and y to particular values, set those particular control lines to a particular value, which will then do an operation on x and y. So I've shown here in this table the various operations that arithmetic logic unit will perform. So we can do a transfer of x, so we can simply move x to the output. We can increment x, so we can do an addition of x and y. We can do an add with a carry in, we can do a subtract with a borrow in, we can do a subtraction, we can do a decrement, we can do a transfer x and y also out to the s. We can do a logical OR, we can do a logical XOR, we can do a logical AND, and we can do a bitwise complement. So we can do these various operations simply by setting those control lines to a particular value. And I recommend you, at your leisure, look at this table and look at the figure in the previous slide and just confirm it for yourself how it operates. It's a really wonderful piece of circuitry, the ALU, but of course the ALU that we have inside our processor, of course, is a lot more complex than that one. So when it comes to our processor of choice, what does the arithmetic logic unit actually contain? Well, the CPU12X core is in fact a 20-bit arithmetic logic unit, so we've got a lot more bitwise additions and subtractions and things that we need to do. It's capable of 1 large operation or 2 smaller operations during a single instruction cycle, so we can do additions and subtractions on single cycles. Okay, that can either be a single 16-bit operation or 2 8-bit operations at the same time. The functions that we can do in our ALU are controlled by the instruction queue via the microprocessor control section. So the control is simply taking the values from the instruction queue, running them through the instruction decoder, and then of course setting the various control lines on our arithmetic logic unit to implement that particular action that we want it to do. CPU12X core boasts the fastest arithmetic logic unit ever implemented on a Motorola or Freescale general purpose microcontroller unit. And of course the operations undertaken in the ALU directly affect the status of the condition code register. The CPU12X ALU is capable of performing many different functions, including 8-bit and 16-bit subtraction and addition, binary coded decimal addition, 8-bit and 16-bit multiplication and division, bit tests and manipulation, so we can do compares, bit clear, bit sets, we can do ANDs, XORs, ORs and exclusive ORs, we can do 2's complement addition and subtraction, we can do 1's complement negation, we can do many, many different operations on many, many different registers and also directly on memory locations. So not only do we have a great arithmetic logic unit that allows us to do so many different things, we also have many, many different addressing modes that allow us to do things straight with memory without having to load them into the core and then process them. We can do it straight into memory. So it's a great little arithmetic logic unit, and it's a great little processor, and it's very powerful considering the costs and the size of it. Okay, one of the most important features of a microprocessor system, of course, is its buses. The buses are effectively a group of wires responsible for doing a common goal of some kind. So when it comes to a microprocessor, effectively we have 3 different types of buses. We have an address bus, a data bus, and a control bus. When it comes to the address bus is responsible for transmitting addresses outside of the microprocessor. So those addresses that come out of the microprocessor are basically responsible for turning on a particular device that is memory mapped into our memory. So it may be to turn on a particular memory element in our RAM, or maybe to turn on a particular I/O device or whatever. But basically it contains the addresses to turn on particular elements in our memory map. The address bus can be 16 or 32 bits wide, depending on the kind of processor that you have. The data bus, however, can be 8, 16 or 32 or even 64 bits in size, and it is primarily responsible for transmitting data in and out of the processor. So whenever we activate a particular memory location with our address bus, it is then the data bus that either transmits that data to that device or reads the data back from that device into the microprocessor. So the data bus, it is the size of the data bus that effectively defines what sort of processor it is. So if you have a processor with an 8-bit internal data bus, then it is considered an 8-bit processor. If you have a processor with a 32-bit internal data bus, then it is considered a 32-bit processor. Our processor of choice is a 16-bit processor because it has a 16-bit internal data bus. When it comes to the control bus is responsible for transmitting those external control signals. So these can consist of signals like a read-write, the clock, or the interrupt signal. So these various control lines are then used to drive those external memory mapped devices. So just to do a very quick review of the processor, when it comes to the way that the processor operates, effectively we simply fetch an instruction from memory, we load that instruction to the instruction decoder, the instruction decoder then executes that particular instruction. The instruction may take a few clock cycles to operate, okay, depending on what it has to do. If it's a multiplication, it's going to take 10. If it's simply a load or a store, it could take 2 to 3, depending on whether it has to fetch the operand or whether the operand is immediately supplied to it. So the instruction may require the use of a register, the ALU, or memory in order to complete its operation properly. Okay, so for example, if the instruction was an LDAA port A, then this would require the process to fetch an 8-bit value out of memory in the location that's referred to by the variable port A and put that variable, or that value, so to speak, in accumulator A. Steps involved completing the instruction successfully would then be give the memory interface the address of port A from the instruction. So the address of port A is actually with the instruction. So it gives that to the memory interface section. Echo the address of port A onto the address bus. So that simply comes off out of that I/O device onto the address bus. It simply sets the read line high. It reads the value from the address of port A via the data bus into the temporary register. And then it simply moves the value read from port A, which would probably be in some memory address register or some memory data register, simply moves that value from the memory data register into accumulator A. So on this figure here, I've actually showed you the overall system. So this shows you the entire systems of our processor of choice. So you can see we've got the CPU 12 core up in the top left hand corner. We've got the RAM sitting above it. We've got the voltage regulator, make sure our voltage is nice. Got our phase lock loop in there. We've got our interrupt subsystems. We've got our our various input-output on the right-hand side. So these are all our input-output subsystems. So we've got our general purpose input-output down the rightmost side, and we've got our other subsystems sitting next to it. So our serial subsystems, our pulse width modulations, our CAN, our enhanced timers, and our SPIs and so forth, all sitting next to it. So if you should require any further assistance, please do not hesitate to ask your demonstrator. Post a question on the forum, email me, the convener, or make an appointment to see me. But please ensure that all your questions get answered one way or another.